if that's okay. Thank you. So today I want to talk about how the surface temperature of the moon may influence our measurements thanks of normal albedo. And for this analysis, we're using the Lunar Orbiter Laser Altimeter, which is also referred to as LOLA. So we know that the thermal environment on the moon is quite extreme. The moon rotates relatively slowly. It also doesn't have any appreciable atmosphere. And as a result, the temperature variations experienced in the equatorial regions can actually rise on the order of 400 Kelvin between midnight and local noon. And these temperature variations can cause important spectral changes in rock-forming minerals in the near-infrared wavelengths. So temperature variations can control the size and the shape of the crystallographic site, and this controls the position and the depth of major absorptions. So for example, here are a variety of pyroxene spectra that are plotted that were collected at a variety of different temperatures, ranging from colder temperatures shown in blue at 80 Kelvin, increasing up to warmer temperatures shown in the red colors at 400 Kelvin. And what earlier lab studies demonstrated for these different minerals is that spectra that were collected at warmer temperatures have broader absorptions, again shown in the red, and then in contrast, samples that were collected at much cooler temperatures, shown in the blue, have narrower absorptions. So as these samples are cooled, the sites contract, and this actually causes an increase in the crystal field splitting energy, and as a result, an increase in the measured reflectance. This phenomena is dependent on wavelength, but curiously, one of the largest changes experienced by pyroxene overlaps with the observation wavelength of LOLA, which is 1064 nanometers. And we can take a look at how the temperature-dependent change occurs for certain minerals, specifically at LOLA's observation wavelength, and that's what's shown here. So on the y-axis, we have the measured reflectance for a variety of pyroxene samples in the orange, and then olivine samples on the bottom in blue. And these are collected over a variety of temperatures. So on the x-axis, increasing from colder at 50 Kelvin up to 400 Kelvin. And so what we can see is that over this temperature range that we're experiencing over the course of the lunar day, we have major changes in the measured reflectance of pyroxene, in fact, about 1.5 times. On the lunar surface, of course, it's going to be a more complicated story. There are a variety of other minerals that are mixed in the surface materials, as well as space weathering effects that actually dilute this strong temperature reflectance relationship. But earlier analysis of some returned Apollo samples by Henriks and Lucy demonstrated that about a 5% change was able to be detected in Apollo samples for temperature ranges that are coincident with variations in temperatures experienced over the course of a lunar day. So 5% variation is on the order of uncertainty for a single LOLA shot, but we've been observing the lunar surface now for about a decade, and we've been able to accumulate millions of individual observations of the lunar surface. And so the primary question that's driving our research is, how does the surface reflectance of the moon, as measured from orbit by LOLA at 1064 nanometers, change over the course of a lunar day, where we have these major temperature fluctuations? And we're interested in this question for two main reasons. One, understanding the distribution of important minerals on the lunar surface, but then also thinking forward to future observations of the lunar surface, really understanding how this temperature can control our measurements that we're able to take. So in order to tackle this question, we're looking at the normal albedo of the surface from LOLA. Again, this is at 1064 nanometers. And then we're tying that to the temperature of the surface as measured by Diviner. And we're specifically looking at data that was acquired between local 0700 and 1600 because this is the time gap where we have coverage of the lunar surface from LOLA. We're binning the data in 1 degree by 1 degree spatial bins, which equates to about 30 kilometers depending on where you are, and specifically from 65 degrees north to south because this is where we experience the largest temperature variations on the moon. So first I'll show the normal albedo of the moon, and what we're looking at is both the far side and the north and the near side, and these transparency gaps are giving you a sense of the overall coverage we have by LOLA over the course of the lunar day. And so as we travel along the screen, we start at 0700, we travel through noon, and then we end up at 1500. And then on the bottom here, we have the diviner day of the surface temperature, again, stepping through time from left to right. And so the overall temperature variation that we're capturing in this in this group is about 100 Kelvin between 700 and local noon. And so one thing that I would like to start with is by looking at between 7 and 8 and then noon to 1 p.m. local time, because this is where we have that large temperature variation. And so qualitatively, what we can see is that the normal albedo for the colder samples on the left appear to be relatively brighter or higher albedo than the globes on the right, where we had warmer temperatures. There's a variety of ways you can look at this data just qualitatively. So another way I like to do it is look at maps as we step through time. So on the upper right here, we have a time tracker of local time. So as we step through, we're essentially increasing temperature, starting at warm, warmer, warmest, warm. So as I step through at this time, I'd like to draw your attention to this red square, and we can pay attention to the normal albedo and how that changes with temperature. So I like to think of it as starting at bright, darker, darkest, dark. And again, one more time, starting at bright, darker, darkest, dark. And so now really being able to quantitatively analyze these changes is something we're interested in. So this is my watermelon plot, I like to say, but essentially what it's illustrating is the overall change in reflectance per temperature. And so regions where this relationship was negative are shown in pink, and anywhere we had a positive change is shown in green. And I'd just like to point out that the green edges are really an artifact of the data we could see in some of the earlier plots. And so this is actually illustrating that over the majority of the surface, we're looking at this negative change in reflectance with an increase in temperature. And so here I've changed the scale where we're basically trying to highlight the regions where this change is greatest. And so those are highlighted in the yellow color, where we have the greatest change in albedo with temperature. And so there are a couple of main conclusions we can see with this plot. The first is that LOLA appears to measure a higher surface reflectance when the temperatures are colder. So again, that's at the 7-8 a.m. range. But overall, this change is very, very small. It's only typically about 1 to 2% change. Overall, that delta R, delta T relationship is ranging from 0, so no change, to -1. And this is multiplied by a factor of 1,000. As I sort of started the talk, one of our interests in looking at this was thinking about the mineralogy of the lunar surface, and if these temperature-dependent spectral changes might be correlated with the mineralogy of the surface. So now below this plot, I've shown the Orthopaedic scene map for the moon by Lamellin's work. We're looking at the same spatial projection and spatial ranges. And so qualitatively, maybe there's some sort of correlation between where we see those larger change in reflectance and temperature, which again are in yellow, and where we have increased areas of Orthopaedic scene. But quantitating this relationship is something we're working on now and trying to understand any inherent instrument effects that will also be picked up in this analysis. So that's very much ongoing analysis. So overall, to conclude, we do appear to observe a higher albedo as measured by LOLA when the temperature of the moon is lower. This is consistent with the laboratory measurements of pure minerals, which I started out showing. It's also consistent with ground and spacecraft observations of other airless bodies. But overall, the magnitude of this change appears to be very, very low, on the order of a few percent, 1 to 2% really. And thanks. And this is due to the fact that there are lots of other minerals mixed on the surface and some space weathering effects that dilute this strong temperature spectral relationship. And ongoing work is focused on determining the root of these changes, how it relates to the mineralogy of the surface, how it relates with systematic instrument artifacts. But we're really interested in this idea when thinking about future science of and from the moon. There's been a lot of talk this meeting about volatiles on the moon and other airless bodies, and lots of times our evidence for frost or for ice comes from surface reflectance or enhanced reflectance. So as we're able to get more precise and more high-resolution observations in the future, it's really important to think about how temperature can influence our measurements. Thank you.
All right, are there any questions?
So, thank you. On the first thinking, it totally escapes me. What's the physics? Why is the the albedo changing with temperature? And then, one possible way out to me is, do you have a plot of the instrument temperature? What else is changing at the same time?
Yeah, so to touch on the first part of your question, as the temperature is decreasing, we actually have a site contraction, and so this causes an increase in the crystal field splitting energy, which can increase the reflectance of the measured sample. So this is explained in detail in some of the early papers by Singer and Rausch, who did these really fundamental experiments that I showed at the beginning. And then your second question about the temperature of the instrument. No, it does not seem to be correlated. All the data that we're working with has been calibrated to take out any of those effects. So, yeah.
Anyone else?
I have a quick question. So to me, it looked like on your plot, the dichotomy that you were showing was mostly differences in albedo. And so it looked like the Maria had smaller changes than the Highlands, and that the biggest difference between those two is the albedo. And so how can you also pull out the albedo effects of what you're seeing and really understand how independent of a measurement you're seeing?
Yeah, that's a great point. So what we're doing is looking at the relative change by taking into account the intrinsic reflectance properties of these different materials, because that's really important to understand. So we're doing that with both the albedo of these different units, and then also a lot of the work by Lamellin et al. Looking at the different mineral abundance. Thank you.